This time we're going to talk about the Brayton cycle with reheat and intercooling. We have been talking about how we can increase the thermal efficiency of our Brayton cycle. One way is by adding regeneration, and that allows us to decrease the amount of heat that we have to add to the cycle. And the other way that we can increase the thermal efficiency is by increasing the work net out. And that work net out is equal to any of the work outs minus any of the work ins. So let's look at increasing the work out, or the work net out, by just increasing the work output. And for this, we're going to use multi-stage expansion with reheating. So in a Brayton cycle, you've got an expansion process and a turbine, and let's just give it some arbitrary numbers 1 and 2. So I'm expanding from some P1 to some P2, and because it's a turbine, I'm getting some work out of it. Okay, well, remember that I'm making air standard assumptions, which says that all of the processes are internally reversible, and I am also treating this cycle as if it's operating at steady state. So any work that's generated or any work that's associated with the process is steady flow, reversible work. And if you remember from Thermo 1, we have an equation for that. If you need a refresher, there is a video on steady flow reversible work that's accessible to you in the Thermo 1 review videos. This guy is in sign convention, which is what you're probably familiar with from Thermo 1, but I can easily kind of tease out that W term and put it in subscript convention. No problem there. Another assumption that we're making is that the working fluid is air and it behaves as an ideal gas. So we can use the ideal gas law. And I can use that ideal gas law to express that specific volume and put it in terms of pressure so that if I wanted to, I could integrate it. And what I see is that this temperature term here, well, if I keep that temperature term elevated from state 1 to state 2 during the entire process, I can maximize that work output, and that's what I'm going to do. And the way that I'm going to do it is by multi-stage expansion and reheating. And what that means is I'm just dividing up that expansion stage into 2 expansion stages. So all right, so what I've got here, I've got 2 turbines, and then I'm expanding. I come in at state 1 and I partially expand it, but before I fully expand it all the way out to P4, I'm going to heat it up a little bit. So I'm going to heat it up halfway through. So if I'm comparing the top diagram to the bottom diagram, I'm looking at the same inlet and outlet pressure. So this pressure that's circled is the same, and these pressures that are circled are exactly the same. And the other thing to make sure that you notice is that, as with any of the heat exchangers that we've been analyzing in these Brayton cycles, because all the processes are internally reversible, I don't have any pressure drops across components, across any piping or components like heat exchangers. So P2 and P3 are equal to one another. All right, we can also do the same thing with the compression process, and this would be multi-stage compression with intercooling. So in a Brayton cycle, you've got a compressor, you've got air coming in, state 1 is being compressed to state 2, arbitrary numbering, of course, and you have to put some amount of work in to do this. Well, I could divide that compression process into 2 parts. And so I start to compress it, the temperature starts to go up, but as I come out, I partially compress it to state 2 down at the bottom. I partially compress it to state 2, temperature goes up, but then I reject some heat to keep that temperature down because I want to keep the temperature down to minimize that work input that's required for this compression process. So similar kind of thinking is what we talked about with multi-stage expansion with reheating. And just keep in mind, when we're comparing these 2 diagrams, that these 2 circle pressures are the same and these 2 circle pressures are the same. And also there is no pressure drop across that heat exchanger. So P2 and P3 in that bottom diagram are exactly the same. So what this looks like all put together, if you had a Brayton cycle with reheating and intercooling, it would look like this. So you've got this combustion chamber between 4 and 5, and of course if we're going to model it, we're going to model it as a constant pressure heat addition process. So that's my QN, but oh, I've got another QM because I've got multi-stage expansion with reheating. So I've got reheating between 6 and 7. And then you see on the compression side of things, I've got multi-stage compression with intercooling. So I've got a Q out there. And I'm not quite done yet labeling my Q ins and Q outs because I need to close that loop. So state 8 is where you in reality have an exhaust process, and we're going to model that exhaust process as a constant pressure heat rejection process. So I've got another Q out there. I also have some work inputs that are required to run those compressors, and I've got some work outputs that are generated from the turbine, from the expansion processes. And when I calculate my thermal efficiency, I just need to make sure that I'm taking all of those things into consideration. So the work net output, I've got to sum the work from both of those turbines minus all of the work required to run those compressors. And then my QN on the bottom, I've got 2 QNs that I need to take into consideration. I've got between 4 and 5 and between 6 and 7. I could also put that thermal efficiency in terms of Q out and Q in, and of course I've got 2 Q outs that I need to worry about there that I don't need to. I need to make sure that I do not forget about. So. All right, well, I hope that was helpful. We are wrapping up our discussion on gas power cycles. So let me know if you have any questions, and thank you for watching.